All right, quick test. Can those in Calgary hear me? Quick sound check. Quick sound check. Good to go. Thanks, Darren. All right. Ooh, that's a lucky Jiffy. All right, let's get started. Hey, how's it going? I'm new for you, but I've been here for a little while. I was just on vacation, so you haven't seen me yet. Normally, I lecture kind of every week. My name's Carl Jensen. I also mentor here, mostly on Mondays and Tuesdays. So that's usually when you should expect to see me. You've been very fortunate to, I think, have some great lectures up until now. Any highlights? Maybe not. I don't know. I'll try and kind of live up to that standard. But since this is our first time meeting, I do want to kind of mention a few things. I like feedback. I like to be told sort of how things work for people, whether or not it's we all have different styles of learning, whether or not we can label them or not. But I just like to hear how you interpret this material, what you like about it, whether or not it's too fast or too slow, the pace and all that. I'm going to do my best to keep up with Calgary, so I'm not sure if this cohort asks a lot of questions or not. The last one definitely did, but sometimes it doesn't, and I don't think it's one way or the other. I think it's just cohort personality, right? Every cohort has their own personality, so sometimes that happens, but I'll try and keep my eye on Slack. Is someone else watching Slack from Calgary? Yeah? Well, great. So I got a backup. So what's your name? Sorry, I asked you just as you put... Sorry, Kira? Kira, thank you. So Kira's going to back me up, Calgary, so if I'm horrible at it myself, at least I have a little bit of a heads up. I see this thing. This must be Sam. He's really into Arduino, and it's a great idea. I've thought about it too. I've thought about like having a big red light here so that people in remote cohort can hit a button and it'll flash on, and we get it immediately. I think that's a great idea, and I think this is a good first step, maybe. I don't know. I don't know how to set it up though. It looks like it hooks up to this computer here, maybe through USB, and then you have to run some apps. So I'll get him to show me that. I don't. Does it work? Well? Yeah. Okay. Cool. So I'm sorry about that, Calgary. I'll have to learn how to get that hooked up so we can at least get. I really want to see it in action. Actually, I probably shouldn't touch it because it's held on literally by like the worst tape that you can buy. Okay. So I'm here today to talk about databases. With everything that we teach you, or I guess I feel like I come up here, I talk to you, I tell you things, and whether or not you learn or not, I don't have a ton of control over that. So I just hope that you learn these things. And the thing I'm gonna hope you learn about today is databases and relational databases, and the language we use to query these relational databases. Last Thursday, you were introduced to a type of database. Does anyone want to volunteer what that type of database is? Mongo. Yeah. So that's the implementation name. There's lots of different key value store databases or document store databases like that, and so Mongo is one of them. And it's an interesting way to store our data. It actually comes from sort of this massive sort of onset use of JSON in our applications, a way to structure our data. It'd be easy if we just store our data in the same way that we use it in our app, right? So MongoDB comes out, NoSQL comes out, and kind of is quite popular for a little while. But I think that sort of honeymoon has sort of started to die down a little bit. I think that people are starting to realize that it's not the right tool for every single application that you want to build, and sometimes we need to go back to relational or SQL databases to get the tool that we need for it. These things are 50 years, like these relational databases, the design of these are 50 years old. They've been proven. We've used them for a long time. We've scaled them up, and they're used on the largest largest websites, the Facebooks of the world, to this day. So it's all about solving this problem of data persistence, right? That's why we introduced Mongo and NoSQL to you, so you could store, so you could use the tweets, and when you restart your server, the tweets are still there, the ones that were created. That's a pretty powerful thing for a web application. Can you imagine if your web application lost all its data every time it restarted? That could come from a crash or just someone ripping out a outlet cord or whatever, right? So we need to persist our data, and it doesn't have to be as complicated as Mongo. It doesn't have to be complicated as a relational database, but we get a lot of benefit from that. So one of the ways that we might store our data previous to these systems, or not necessarily previous, but before we need such a solution, we might start to store our data in a certain format like CSV, JSON, or XML. So this was quite popular, right? You store the contents of your database instead in a CSV file. So every time you load your server, you read this file. It loads up the data into memory in your server, and then you're able to interact with that. And every time you make a change, you rewrite this file to the file system. Well, you've got some concept of data persistence, right? But there's problems with this. So let me show you my first example. And let's see, got nothing in Calgary. Okay, good. I'll show you my first example here, and it's under a folder called persist. So I sent out my notes. I try and send out my notes the night before. I forgot today because I'm a little bit out of practice. It's been a few weeks, but I sent them this morning as soon as I logged in, and I've also sent the afternoon one. So all of my notes exist on GitHub. I put them under my repo. I try and keep them updated. If I find errors, I update them and I push those changes. So if you're looking for any of these notes, you can find them there. And there's also definitely going to be notes from all sorts of other lectures that I've done as well, and things that you've done in previous weeks, so CSS and all that type of stuff. So if you are interested in maybe a different perspective on some of these lectures, feel free to poke around in here. It's available to everyone. Okay, so we're in SQL Intro today, and I've got a bunch of code, maybe stuff that I want to show you, the code that I want to share with you, and then I've also got my notes, and so the notes are in the README file here, and these are sort of broken down really in the same order, the same structure as what I'm telling you and what my slides follow. So here we are with data persistence. What I want to do here is show you an example of how we can save a file to the server's hard drive, and then every time we reload the server, we read that file and load up the data. Okay. So this is just that same repo, but I've opened it in Visual Studio Code now. And I've got persist here. This is the directory for the persistence code. So index.js contains all of the code that I'm going to be showing you for this example. And it starts off, we don't need to fully understand every single line. I think that can be overwhelming, right? My goal is to show you what's possible and to kind of give you an idea of what the concepts are. The actual implementations themselves, I expect that you'd have to come back, review this code, and potentially even ask questions of a mentor throughout the day. Like that to me is that's not a bad thing. Okay, so we're going to start off. I've got some basic node imports here. I'm importing things to do with the file system and things to do with the path, so I can actually interact with this file system. We've all done this already. We've required Express and built an Express server, so that should be relatively straightforward. Same with body parser. We know about that. And I need to use both of these libraries in order to create this web server. I start up my web server here, and I've got this little helper function. It's using some ES6, so it looks a little bit weird, but this is just an arrow function that it takes in JSON, and it returns to me a formatted version of that JSON. Rather than all on one line, it breaks it out, and it shows it to me in a nice way. I think that's a little bit nicer to show a user. So I've just got this little helper function that I pass that in, the JSON into, and it returns a stringified version. Nothing fancy there. All right, so here's the first real kind of interesting part here. I'm creating a new variable called database, and I'm pointing it to path.resolve. So whatever path.resolve returns, that's going to be the value of database. So this is actually a string that points to the file that I want to write to the machine. And that file's name is students.json. Okay? Within Node, any file that you run in Node, if you put _dir name, that represents the directory that this file was in. So if this file is in print working directory, if this file is in the persist directory here, and I print the working directory, what I'm going to get from dir name is this whole path right here. So that's kind of nice. It's just something that Node provides to us. It doesn't exist in the browser, but it exists in Node. So I've started off with this, and it's the same as me saying, or very similar to me doing this. Oops. Oh. There we go. Okay, so it's very similar to me doing this, where I just create a string that represents the path to this file. I've kind of screwed that up. But the problem here is that if someone else uses this on their machine, it doesn't really work, right? Because this is pointing to the location of this file on my machine, and if you clone it to some other directory, then this path would change. So we want to make this dynamic, and we use path.resolve for that. That's also built into Node, okay? So I'm just building up a database location so that when I save a file, it ultimately saves a students.json file into my persist directory here. When the server runs, I'm going to check to see if that file exists first. And if it doesn't exist, so if it equals false, then I'm going to do this really kind of hacky way to create a file. It's open and close a file. That's kind of one of the better ways I found to do this, is to create a new file by just opening it with this name, writing nothing to it, and then closing it. Well, now that file exists. So I can read that file. I read that file right here. And when I've read that file, what I do is I take the result of it, I convert it into a JavaScript object. It's an array that represents a whole bunch of different students. I'm going to use my body parser here, so we won't worry about that. Here, when I get /, so when I do a request to the server to get /, I'm going to get back a list of all the students as JSON. When I post to / students, I'm going to pass some data in on the body, including the name, the email, the phone, and the GitHub. And I'm going to push that onto the students array, and then I'm going to write the file. And that's actually where my persistence comes from. Is every single time someone posts to my web server a new student, it will write it'll write the contents of that student array to the file on the drive. And that's it. And then just tell the app to listen. So let's just show this as an example. Node index.js. All right. Logo is 3000, so we're getting an empty array here. That makes sense. There are no students yet. And what I want to do is make a post request here, and I'm going to use curl to do it. Got to open up another tool, another command line. Everyone found that out the hard way, right? If you want to run curl and a web server at the same time, you got to have another tab open. Yeah, so I'm in this directory already. And I'm going to, I guess it doesn't really matter what directory I'm in. I just need to make this request. And what I'm going to do is I'm going to post a bunch of data. The name, the email, and the phone number to localhost students. When I hit enter, it actually adds that thing here, and I get an output that says updated the persistent data store. So now I can close the server, and I can look and see there's a students.json file. So every time I start the server, it's going to load this file, and it's going to load that into memory, and I can modify that. And every time I modify it, it's going to write it back to the drive. So I've got data persistence now, right? Why would I need a database if I can just do this? I gotta hear it louder, a little bit louder if I, yeah, go for it. Okay, hundreds of thousands of entries. That's a great response, right? So as this scales up, obviously reading a larger file every time is going to take longer, and writing a larger file every time is going to take longer. So this is a very naive approach to larger sets of data. It'll work with 100 entries, 200 entries, maybe 1,000 entries. But when you get into the millions of entries, this is a really bad approach. There's also another thing that we really need to think about when we're trying to when we're doing it this way. Something that would get in our way. Yeah. Duplicate data. So duplicate data, how does that manifest, or how do you see that happening? Mm-hmm. Okay, so if we have users, I'm just going to repeat for Calgary. So if we have users that are changing information, then when they change that information, am I duplicating that information? Is that I would say you would probably write code to try and prevent that, but there is something coming from that actually is a problem. Let's say two users are trying to write their data at the same time. Does the server write mine or yours first? And it writes after it writes yours, does it have yours updated and then appends mine to that, or does it just write mine over top of yours? And this is kind of a problem, is that we can't easily have multiple writes to the same data. Yes, Calgary, great. So no relationships. No relationships. I guess that's kind of true, except I can define relationships in JSON including document stores. So maybe I have something like this, ID1. The name is Feb04. What does this represent now? Maybe a list of cohorts, right? And a cohort has many students. So I could technically kind of create, I could put a students. I could put a student into this array, and now my association is that a cohort has many students. I am able to define that, although we don't really want to be doing this. This is a tough way to do it because that's gonna we're gonna have a lot of duplicated data. For example, if we do relationships like this, let's say in this case, yeah, a cohort only has, or a student only is in potentially one cohort, right? But there are situations maybe where students belong to many cohorts or whatever it is. And in that case, you'd have the same student data in a whole bunch of different places. This is kind of a problem. So there's issues, there's things we want to solve, and databases help us with this. One of the things is, let's reduce the duplication of data. And so I'm going to show you how to do that with relational databases. The other one was that we can't have two people writing the same data at the same time. Well, with a database we can. MongoDB is a really fancy document store. This is a very non-fancy document store. This is a really ugly, kind of useless document store. But MongoDB is a useful document store because it allows us to have requests come in at the same time, and it will have the data reflect all of the changes rather than just the last one, let's say. So this is one of the problems with writing directly to files, and so we, in order to scale, we want to use databases. Does that all make sense, why we're doing it this way? Okay, good. All right, so we remove the duplication of data. I'm going to show you about that. We also have a robust query language. So this is SQL. This is a language that we use, special purpose. Might call it a domain-specific language. The domain is database querying. Sometimes you'll see DSL as the acronym for that, domain-specific language. Does that make sense? Yeah? And DSLs can be written for anything, for testing. We see lots of domain-specific languages. Just a language that's really good for a specific purpose. We find that JavaScript is good for some things, but not everything. SQL is really good for asking databases for data. But I couldn't necessarily build an entire web app in SQL, right? It's just a part of it. So we have a robust query language we want to learn. And then what I find really cool about relational databases when I'm teaching them and talking about them is that they accurately model reality. So today's reality, the one that we're going to be talking about, is the reality that we're in today, which is students, cohorts, assistance requests, assignments. These are all the things that we need to store data about, similar to what Compass does for us. Right? It's not the exact same database schema that we use at Lighthouse Labs and Compass. That one I looked at, way too complicated. Hundreds of tables. I've kept it down under 10, which is I think a good number to teach with. But 2, not a good number to teach with. So had to kind of find the right level, right? Okay, we're talking about database design first, and then we can talk about how we query the database for all of our data. So I said reduce the duplication of data. How do we actually accomplish that goal? So this is database denormalization. That's the term we'll use. And I've got an example here. What's the problem with this table, this students table? Repetitive information. I got April 09 in there 3 times, right? So let's talk about a scenario where this might hit you, or I guess catch you off guard. We don't let you do this, but let's say that in Town Hall week 3, you've now been together for 2 weeks, and you have an opportunity to get together and talk about and name your cohort. We have that cohort every cohort has a personality, so based on that, maybe you have some inside jokes or something. You come up with a name for your cohort, and then you submit that to us, and we have to now go and change that in the Compass database so that every thing that said February 04 before now says, I'm going to leave it up to you, right? That's kind of a problem. I got to go change every student's cohort name now to reflect that. So I have to actually make sure that my software or whatever it is knows to do this and goes through, and for each student that's a part of that cohort, update that row. That is a lot more complexity than should be necessary, and I think it could lead to writing bugs, right? The more code we write, the more bugs we have, and so we want to reduce that. We can normalize our database. This is how we want to structure our database. It goes into the design of our database. The solution to this problem is in the design of our database. Instead of having the cohort name specifically in the students table, what we'll do is we'll keep track of information about the cohort in their own table. So you have a students table, it's only information about students. And you have a cohorts table, it's only information about cohorts. And then we can use a reference, an ID, a unique identifier, to point to that information instead. So now it's a lot simpler. If I need to change the cohort name for the February 04 or February 12 or whatever cohort, then I just go into the cohorts table, I alter one row, and now every single student that pointed to that cohort that had an ID of 3, the name is changed for them as well. That's cool. To me, that's really cool. The reference shouldn't really change unless the cohort changes, or unless the student actually changes cohorts. The ID that we give to that cohort should never change. And if the cohort moves into the next cohort, then they should get the cohort ID 4 instead, and then it will just point to that name. Okay, so this is database normalization. This is how we reduce the duplication of data, and this is why we have to learn about these databases now, because we have to learn how to then put the data back together when we actually need it. As we go through the design of this database, we're going to be using a tool called, or I guess it's a diagram type called an entity relationship diagram. You don't have to read this right here on the side. I'm going to bring that up in size. We'll kind of investigate it, but this is kind of what it looks like. Each of these boxes represents a different table in my database, and it also tells me what columns those tables have and how they're related to each other. So I'm going to show you how to build these things. Before we do that, though, I want to make it as easy as possible for you, and so I'm going to show you a convention that you can use, because naming things is not easy. And so if I can just give you sort of some tips on how to name things, and we can get that out of the way and focus on designing the database. So first convention we're going to use is it's snake case. Sometimes we use camel case, which is the word starts with lowercase, and then every word, there's no spaces between them, but we uppercase every word within that variable name or whatever it is. That would be camel case. We're going to use snake case for this. Snake case is everything is underscore, and all the words are separated by an underscore. They're lowercase, and all the words are separated by an underscore. Does that make sense? Okay. So if we learn this convention, we get a few benefits. One of them, everyone on our team for the midterm will know what our tables are named already, because they would have named them the same thing, right? Or at least close. So convention's really useful for this. Convention's useful for group work. It's useful for sort of giving the answer without having to think a lot, right? So the convention for every table, we're going to identify some sort of thing or entity that we're storing information about. And so the entity that we're storing information about today would be a student entity. And we care about it. The information we care about students would be their name and their email, their phone number, maybe the GitHub information, whatever we store about students, when they start the program, when they end the program. That student information is going to go into a table called students, right? Because there's lots of rows, there's lots of students in there, so I'm going to pluralize it. I think that makes more sense. So it's not the student table, it's the students table. If this was 2 words, assignment submissions, assistance requests, I would put an underscore in there. So it would be the assignment underscore submissions table or the assistance underscore requests table. Does that make sense? Okay. Every table that you create should have a primary key. This is going to be that unique identifier for every entity. So every student should have their own ID. We're going to call every single primary key that we put into all of our tables today ID. We're just going to name it ID and not think about it after that. We're not going to call it student underscore ID. That's redundant. It's in the students table already. Does that kind of make sense? And I'll show you why that redundancy comes later, where you're like, oh yeah, okay, now I see why you wouldn't bother doing that. It's too much typing in that case, right? So students.id would be a way we could access ID. We also have at the bottom there something called, okay, so I guess I'll go the column names quickly. Name, email, start date, end date. Those are just camel case. We're going to talk about types soon because they will have their own types as well. But this could be anything. This is kind of up to you. And as you see in my ERD that I've created after this, you're going to see all the different kind of naming that I'm doing. The last thing that I want to call out specifically is the foreign key, and this is how we identify a relationship. If a cohort has many students, then a student belongs to a cohort. The way we define that relationship is on the row of student data. Right? That's it. We just give them an ID, points to another table. And so that's what we're calling a foreign key. It's a reference to another table in the database. Okay. And again, this is all in my notes. So if you want to see it again and a little bit slower, then it's a good play for it. So we have these relationships. A cohort has many students is a one-to-many relationship. There's one cohort. Cohort has many students, and so we want to decide how we actually create these relationships, or what side the foreign key goes on. That's our goal, is to figure out what side, which table do we put that foreign key in. The foreign key is on the many side. That's the rule. When we say that a cohort has many students, what is the many side of the relationship? Students, thank you. Yeah, so students is the many side. Therefore, the foreign key has to go on that side of that relationship. Okay? That's it. That's it. Now, 50% of the time, I still come up to students who are planning their midterm, or maybe actually most likely it's the Navy project that you'll be working on today. When you create your own ERD, and 50% of the time, it's okay. Is this foreign key on the right side of the relationship? What side is the foreign key on? It's okay to get it wrong. It's no problem. We'll help you. We'll help you with that. But after today, this should be your mantra for relational databases. Foreign key is on the many side. All right. So then we got this idea of join tables as well. I can have many-to-many relationships, and this is where things are going to get a bit more, and we're going to step it up a little bit in complexity. The way that students and teachers are related within this reality is through assistance requests, right? When a student asks for an assistance, we could create a new assistance request. When a teacher accepts that assistance request, they are now tied together. And a student can ask for many assistance requests and get assisted by many different teachers, and a teacher can assist many different students. So what we do in order to create this relationship, because we can't put more than one value in that foreign key, right? If I go back here, this student can only have one cohort. So we have this third table in between students and teachers. Students is just a list of students with their IDs. Teachers, a list of teachers with their IDs. And in between, every single request that's created, we're going to create an entry in our database for this. It's going to take an ID from a student, an ID from a teacher, and that's how we're tying them together. Does that roughly make sense? Okay. So we do this for our many-to-many relationships. We add a join table. It's really good to call them what they actually represent. You could call this the students-teachers table if you want. But that doesn't really tell us what it is, because there's other data that goes with it. And that's actually what's kind of cool about these, is an assistance request isn't just a relationship between a student and a teacher. It comes with a whole bunch of other metadata and things that we can use to help maybe give students more information, or administrative staff more information. In this case, when was assistance request created? When did it actually get started or accepted? When was it done? We can actually start to look at these. When we grab enough data, we can look at this table and figure out how long is the average assistance request. How long does it take before someone assistance request on average is accepted? We can answer those questions with this table now, because we've added the necessary data for an assistance request. Does that kind of make sense? Yeah. Any questions about this? I know we're going to try and go through more examples here, and with the Navy stuff, you'll have to do your own join table. Okay. All right. So here we go. Let's do a quick ERD. Draw.io. Now, I'm going to draw.io. It's the best online tool I found for drawing entity relationship diagrams. But it's not the best tool that I know of to write entity relationship diagrams. For me, a whiteboard is the best tool for creating these diagrams. But because I'm teaching you, and it's kind of the screen is here, and it's easy to send that remotely to Calgary, this tool is pretty good for it. And I'm going to try and show you some tips that I found that make it less aggravating to work with. But really, if you're drawing an ERD, a pen and a paper, a whiteboard are just as good as this, just because it's a kind of cloud-based collaborative thing, which is, it's not really even collaborative because I don't know if I can see live edits. Maybe I can. I haven't even gone that far. I use it mostly for this. I draw them out usually when I'm doing it myself. Okay. So as we look over here, they're going to give us a whole bunch of different options for because they don't just support entity relationship diagrams. You could draw class diagrams and sequence diagrams and all these different other types of diagrams that exist in the software development world. The one we care about today is this entity relationship diagram. So I'm going to drop that down, and I'm going to look at these different tables that they give me a template for. The one that I like the most for this is this third one right here. I like that it separates the primary key, and then it actually allows me to call out and to tag things as a primary key or a foreign key. So I'm going to stick with this one. This is what I'm going to use, and I just drag it over. Just put it here. All right. I guess I can probably, use that zoom instead. It's probably a little bit better. If I hold down space, my cursor changes. It's kind of hard to see. That's just me hitting space. As I hit space, I can now drag this thing around rather than just moving my cursor. This is kind of useful. As the diagram gets bigger, I want to be able to reposition it. So learning these shortcuts is an important part of this for me to make this tool useful, right? All right, so what's the table I want to create? We're going to call it students. And a students table, it's going to have an ID primary key because everything is going to have a primary key ID. That's the convention. Some of the data the data we want to store about a student, their name. I hit tab there to switch between these. It's a little bit nicer, I think. And now I can just type in here, put down a phone number, hit tab, email, hit tab, delete that last one. I don't even know why they put that little one there. If I want to add a new column right now, I found that instead of doing this like Control-C, Control-V, and then trying to drag this back into this, that doesn't even really work, right? I can just select an item in here and hit Command-D, and that's actually just adding a duplicate row for me. So once I learned that, this tool stopped frustrating me as much as it did before. That and actually dragging the arrows to connect things together could be a nightmare. Let's give it a start date. Let's give a student end date. And the last thing I want to give them right now, I guess, would be a, not find. That's Command F, not Command E. A cohort ID. And this is a foreign key into another table, so I'm going to label it as such, right? Now, if I've done this, I should probably take this table and duplicate it, so it's Command D again. And now it's just going to be a cohorts table. And the cohorts don't have a phone number, so I'll delete that. I'm just using the delete button on my keyboard. Delete. Cohorts have a start date and an end date. Something like this, maybe. Maybe fix that, because I'm obsessive. All right, so here's my cohorts and my students. And we talked, why did that not fix? Sorry, you have to watch this. Enter, and no. What is going on here? Oh, this is aggravating. Wow. Yeah, they're both skewed, but like, why? Okay, what if I just do ID? Weird. Okay, well, just typing it in fixed it, so I don't know. All right, so I got these students in the cohorts, and the reality that I'm modeling is this one where students belong to cohorts, and a cohort has many students. And so now is the time where I need to connect these two things together in their relationship. This is the association, right? So what's the many side? Student, yeah, left side students. Students is the many side. It's got the cohort ID. You notice that I just used, I just used the cohort, the name of the other table, cohort, but I didn't say cohorts ID. I used singular there, and I did underscore ID to represent that I'm pointing to a key over here, or a primary key over here. And so we got to go back over to this tool And now you got all these options for lines that you can use to connect boxes together, right? One mandatory, 1 to 1, 0 to 1, many to many. Lots of different options here. And the one that I tend to use, the only one I really need, is this one. I like it. So I'm going to drop it over here. And this is where things get frustrating again, because I've got to take this little crow's foot thing here and this other side, and I've got to connect one side to the students and one side to the cohorts. Actually, I think it's the other way around, right? Because this should represent the many side of the relationship. That's what this means. 3 things, more than one, many, one thing, just one, right? So the many side is the students. I'm going to take that and I'm going to drag it, and I'm waiting for it to go green here because that's going to actually connect it to this box. If I just put it, I want to connect it to this part of the box here so that when I move this around, the thing comes with me. Because as this gets bigger, I'm going to have to move these things around, so I want these to be connected. I got to connect this other side now to this primary key, and look at the mess I've made, right? This is one of the reasons people hate this tool, and it might be because they haven't found out about this part up here. So here, oh, much better, right? So now I can drag and resize and position this a little bit different if I want. Oops, that's not what I needed. So that I find that for these lines, if these lines are getting in your way, it's these tools up here that are going to help you with that, okay? So we've connected these things. This is our relationship. How do we feel about this tool, about drawing these diagrams? Any questions so far? Should I do one more example? Yeah. Yeah, so let me show you that again. Because what I want to do is when I move this box around, I want the line to follow, right? That's my goal. Yeah, so that would be there, and what I meant by green is this thing right here. It's saying it's actually going to attach it, whereas if I do that, I'm not sure. Let's see. Yeah, that attaches it well. That's good. So as long as the box here is green. Yeah, I like the green circle because it's a little cleaner. But yeah, as long as it registers and it connects, and now I can drag these things around and have my lines still match up, so that when I get into a situation where I'm just going to load up from my device in the let's say it's in my notes directory. There's bootcamp.xml. This is the file that I saved from draw.io. I'll load it up again in this window, discard my changes, and here is the actual full ERD for the system we're building today, for the data we're using today. Our students. Can we see that all right? I'm bring it up in size a little bit more, maybe. That might be a bit better. There's our students table, name, age, email, phone, GitHub, start date, end date, cohort ID. And then look, this cohort ID points to something down here. That's the cohorts table. Start date, end date. One thing that I find interesting about this, I don't know if you've noticed, my students and my cohorts have a start date and end date. Is that weird to anyone? Is that necessary? Might not be. Under what assumptions would we make? If we were to remove that from one of those tables, which one would we remove it from first off? Students, okay. And then what assumption are we making? Yeah, and that they start and end exactly with the cohort. That no one is dismissed early, no one quits early, that everyone completes. I don't know that that's fair. I mean, it's 95% fair, maybe, right? But I don't know that it's an accurate representation of reality. I think that cohorts have start and end dates, and students have start and end dates, and those things aren't necessarily the exact same. So in this case, I would actually represent those differently. I would say that when we start a new cohort, we know what the start and end date is. But when a student joins, we know when they started. We don't necessarily know when they're going to end. So we probably don't even have a value for that until they finished the program. Whereas of cohorts, we have the start and end dates right at the beginning. So this illustrates how you might have the same named column in two tables, and they might not need. They're not necessarily in sync. They might not even mean the same things, right? Okay. Here's this join table, the assistance request table. I'm going to have to zoom out just a little bit because, wow, it's just so much going on, right? And this table links 3 different entities together. We've got students, teachers, and assignments are the entities that we're linking together through assistance requests. When an assistance request is created, it's created by a student, so we get the ID there. When a teacher accepts, and it's very possible that you ask for an assistance on a specific assignment. And so we might tag that assignment as well in that assistance request. Maybe it's not about an assignment in particular, so this would just be a null value for this row. This assistance request has no assignment associated with it. Big deal. Some of them do, some don't. That's a fair way to do it. What's kind of cool about this, though, is we could figure out how many assistance requests are created for every single assignment that we have. And if one assignment has twice as many assistance requests as every other assignment, that tells me something about that assignment, I think, is that people think they need more help with it, or that maybe they're confused. Maybe it is a confusing assignment. Maybe it helps us understand where we need to apply curriculum improvement, right? So I think tying an assignment to an assistance request is actually pretty useful. So we've got assignments over here. The assignment has a name, the content for it, what day it appears on, what order it is in, and the duration. When an assignment is completed, a new row is created in our database called assignment submissions. It ties assignments and students together. When a student completes an assignment, their ID goes in there. Which assignment is it? That assignment ID goes in there. We now have a record of completion for that assignment for that student. Well, notice we also have a little bit of duplicate data in there, right? Duration and duration. But how do these differ? Because it's the same deal. I didn't try and trick you here. I believe that these durations are different things and that they don't actually necessarily, it's not duplicate data. So why do you think that is? Why would the assignment submission duration and the assignment's duration be different? Some people work fast. Yeah, I would say that the assignment submissions accurately represents how long it took for you as an individual to do it, and that's going to be real data, whereas the assignment duration might be the estimate that we give to you at the beginning that says we think this takes 90 minutes. Great, but when you actually start to tell us how long it takes and we gather more of that data, we could eventually change the app to no longer care about the assignment duration but actually create an average of student durations for that assignment completion and give you a more accurate average. That would be useful, right? So by storing these 2 pieces of information separately but with the same name, they don't have to be the same name. I'm just showing you it's okay that things are the same name. We don't have to come up with unique names in our within the table. It has to be unique names, but across a couple different tables can have the exact same column. Imagine if you couldn't do that and you had 10 tables and each of them had the concept of a name of something. But now you can't use name more than once. That would be really frustrating. You'd spend all of your time with a thesaurus trying to figure out like synonyms for names, right? So don't worry about that. Name exists here. Name exists here. This is a student's name. This is an assignment's name. It's okay. I hope that everyone feels good about that. Do we need to spend any more time? Yes, please. Mm-hmm. Mm-hmm. Okay, yeah, so Calgary, for the example I have here, I'm linking this foreign key to this primary key here. Is that kind of what you're saying?
Yeah, just on all of them. Like
Yeah. Yeah, and so for me, I do this. I don't really care where this shows up. I could put it up here. It's just a representation that these 2 tables are connected. Oh wow, this is so fun. There we go. So I could put it up here, and it's not linking to the primary key anymore, but it is still, that's still the reference we're using here. The student ID is going to be found, hopefully, in this column here. That is going to be a primary key that we're linking to. And for me, my convention when creating these ERDs is that I take the foreign key here on the many side, and I link it to the primary key column. That's why you see 2 things going to the same primary key, because this ID and this ID, they represent the same thing. Is that, you don't have to do it this way. The most important thing is that the crow's foot is on the right side, and that these 2 tables have a link, a line between them in some way or another. I don't care if it comes over here or down here or down here. This is more just me being obsessive. Yeah, it's just me being kind of overly obsessive about it. Okay, I hope that answers the question. Tim is typing in Calgary. Do foreign keys have to link with primary keys? So what it says there is, do foreign keys have to link with primary keys? No. No, they don't have to. But the good thing about primary keys is that they are by nature unique. That they don't. It's impossible to have the same one for two different rows. And I don't really. A foreign key in I guess a foreign key that was a name or something like that. So I guess, okay, let me put it this way. It's a little too early to talk deeply about indexing and all of the details about how you create other keys that you can use for this. So let's say for now, all of your primary key or all your foreign keys are going to point to primary keys because that is the most common thing that we do. And then those edge cases, let's worry about that when we have the need to actually use those something else as a foreign key. Because yeah, in all these assignments, in your midterms, even in your finals, I don't see it happening. But if it does happen, ask a mentor for some help. And hopefully, as we get through this a bit more and talk about indexing, we can understand why we might not make just anything a key like that, or what we might do to make something a better key. Is that okay? I hope that's okay, Tim. Let me know. For now, yeah, link everything foreign key to primary key. You won't need anything else for this right now. Okay. Yeah, I could draw this on a whiteboard. I could draw it on a piece of paper. It solves the same problem for me, which is that within a group of people, if we want to talk about this, it's a good way to do it. It's a good way to verify, too, that our app satisfies all of the requirements. I can say one of my requirements is that I can list out all the assignments completed by a student on their dashboard page. That might be a requirement. Does this data structure support that? Can I take this data and convert that into a list of all the assignments that a specific student hasn't completed? I can, and I'm going to show you that this afternoon, but I would just vet all these requirements against this data structure and figure out, could I make a query that would get me that data or not? And if I can't, then I need to rethink that this ERD might not be complete yet. Is that kind of a good tip? Okay. And that's for your midterms mostly. Yes. Mm-hmm. When I'm adding a new submission thing for my app. So could you give me an example? Mm-hmm. Mm-hmm. Okay. So the example is, let's say we have these, what was it? The assignment submissions, right? And we have the assistance request. We have the student ratings. If I initially design my database with this data, then I don't need to change the database at all. But if I've made a mistake and I didn't know that was a feature and I didn't write my database for that feature, then what I would do is I would alter these tables. I would add new columns if I needed to. And I might even write a script that would fill in data for existing rows, because let's say I do this halfway through my or a month after I've released and people have started to create assistance requests. Then you might have a whole bunch of assistance requests in there without a rating. And maybe you want data in there, maybe you don't. Maybe you want it to be null, so you would just fill it with null values and everything new would fill in with the actual rating. Maybe you would just, I don't know, do an average or something. Who knows, right? Probably not in this case. But yeah, it's possible that you will need to alter your table, adding new columns as you go through a project if you're adding new features. Most of the time you try and come up with a lot of those features early on. You try and figure out what your database is going to be based on those requirements. And you don't really want to be adding every single possible piece of data because then you never end, right? But you're trying to get it as close as you can for the requirements that you have at that point in time. Databases are not that hard to alter the schema of. We're going to show you a technique tomorrow afternoon to almost version control your database schema. The ability to create a table, and then you'll write some code that would change that table. The nice thing is we can share that code amongst all the people on the team, so everyone will have the same schema for their database, because Everyone working on the same project should have the same database schema on their own machine, right? So we've got solutions for that. That's more tomorrow afternoon, though. Cool. Okay, I'm gonna rip through this quickly, and then we'll take a break. This is the last little bit because we've got to talk about data types. We've got the tables, the columns in those tables, which ones are primary keys, which ones are foreign keys, and the last thing we need to think about is what data does each column hold. Here are some options. They're not all the options. The best place for this is like the Postgres documentation. They'll have a list of all the data types that they support for Postgres. Integer, it's a number. Char, varchar, those are strings, and the limit on a char varchar is that is 255 characters. If you need more than 255 characters, then you want to use text instead. Okay, so text would be a large chunk of data, a large chunk of text, whereas char or varchar would be mostly like a line, like a title or an email or a name or something like that. The date. So it's very important that if we do use dates like start date and end date, that we encode them as dates in the database so that we can do things like search based on those dates. I want to find only the students that are active for a certain point in time. I should be able to find students that started between these two dates. If I use the date type, I do get a lot of this benefit. If I just store the date as a string, February 24th, 5th, 2019, I guess, that's not very easy to work with afterwards. It's also only in English. There's lots of reasons why we don't store our dates as strings, okay? So use date if you need to. If you need to store time, specifically, timestamp would be the data type for that. It's kind of a weird way. Boolean, so I want to store a true-false value. That makes sense. And then small int, big int, and serial. These are all different types of numbers. So I've called out integer. That's the primary type of number that we're going to use. But there's a slight problem is that we've got limits on these numbers, and this is just limits due to the design architecture of computers. A small int has a limit of up to 32,767, or it's negative 32,000 to positive 32,000, essentially. Integer gives you a larger range, from negative 2.1 billion to positive 2.1 billion. So most numbers are going to fit in this range, right? Maybe if I'm using age, I'll use small int. But for the most part, if you're going to use a number, just use integer. Okay? Except for some situations that could catch you off. So let's say that I want to store banking account information for a bank. And I'm going to tell you right now that we don't store money using decimal points. It's inaccurate. There could be rounding errors, even a cent. We don't want rounding errors. So what we would do instead is we'd store $1 as 100 cents. Does that kind of make sense? I didn't say that on purpose. That wasn't a pun on purpose. But so $1 is not 1.00, it is 100, and the column is cents. That's how we would store that information. Now, how many cents can we store before we go past 2.1 billion? About 2.1 billion cents, right? That's $21 million. So if I'm storing this information for accounts, most of us won't care about whether or not the account can store more than $21 million, but some people would care. And so what I would recommend in that case is I would use big int to be able to store, $9 billion worth, or 90 billion, or whatever this ends up being. I guess it would be. Yeah, I don't even know numbers that big. It doesn't matter. Point is that if you're choosing the integer type, make sure you know what values could go in there, and if the number is outside of this range, you need to go up. But don't just go up because it's easy. Don't just make everything a big int because it's easy. You want to make a good decision about this. You want to make a conscious decision about this. So I also don't. The other thing is I also don't recommend using small int for things like ages, just because we're not really worried about space anymore. This comes from a time when 5 megabytes cost as much as terabytes do today, right? Nowadays, space is not really our constraint. So using integer for most things, even small numbers, is okay. Cool? I said we're going to store dates. And so in order to get these dates into the database, we have to follow a format. This is ISO 8601 standard for date definitions. This string here represents a specific point in time. It's April 26, 2018, 9:36:28 seconds UTC time, so no time zone on that. When I take this and I pass this to the database, it now has all the information it needs to store this as like a date object. And when I retrieve this date, I could get it back as this string, and then I could use JavaScript to convert it back. But we just need to use this format because this is an agreed upon way for both maybe JavaScript and Postgres to store dates as strings, or to represent dates as strings. So just keep that in mind. We want to use this format for adding dates to the database. And if you're just adding a day, not a time as well, then you're okay with year, month, day. You could use this in the database. That would be 2018, or I guess 2019 dash 2 24, something like that. So this, if I want to tell the database to store a date, a specific date, then I would just use this. If I need to add the time as well, then I'm adding the time to it as well. Kind of, yeah. All right. We make assumptions about things like phone numbers. We could get into trouble. Other than the second to last one, because I need to put some sort of like European number in there. Other than that, are any of these numbers different? No, right? It's just that there's dashes in between some, and there's parentheses around some numbers. At the end of the day, though, what data type should we use to store this value? I would say that a user could enter their phone number in any way into a form on a website. When we take that, we probably want to store it consistently in our database. So we would probably rip out all the spaces, all the dashes, all the parentheses, and we'd probably end up with something, I don't know, maybe like that. Okay, so what's the problem with this though? If we think about, actually it's illustrated a little bit better at the bottom there, so I'll just leave that. What's going on there? How big is that number at the bottom? Bigger than integer. Thank you. Yeah, exactly. So it is outside the range of an integer. Therefore, I can't store it as an integer. I could do a big int, right? Char would be a specific length string. That could work. The reason I'd want to store it as a string rather than a number is because phone numbers could start with a 0. And if a phone number starts with a 0 and I store that as an integer, it chops off the zeros for me. It doesn't allow me to have leading zeros like that. So I would lose some of the phone numbers. So therefore, I'd want to store this as a string. Even though it is a phone number, I want to store it as a string. Does that kind of make sense? So we have to really think about what data is going in there, what are the possibilities, how they change. And the last thing I'll leave you with before the break, there's some links down here. Falsehoods programmers believe about names. And so here's a list compiled. Things that we inaccurately believe about names, and it's not every single thing, but even if we make one of these mistakes, then someone could be affected, right? So we need to be careful about this when we're designing our databases. Do we have a column for full name? Do we have first name, last name? First name, middle initial, last name? Like, how do we decide what our schema should be? It's really tough. We need to understand the reality we're living in, and usually we don't understand it, so we end up making assumptions that are incorrect. Here are some assumptions people make. Keep this in mind. Assumption people's names do not change. Assumption people's names change, but only at certain events. All names are written in ASCII. People's names are case insensitive or sensitive. Like, none of this is really true or false. It's just the reality of storing this information in a database. So I've got one more link here. There we go. And this one's actually just in general called awesome falsehood, and it's things that we believe to be wrong about all of the reality, right? So things like human identity, falsehoods about gender, or falsehoods about language, falsehoods about phone numbers. Here it is, right? You want to learn about this stuff? You got to go and look at what other people wrote about it. This resource is way more valuable than it looks, because for you to find this out, it could be a bug in software where you're called in the middle of the night to fix, that kind of thing, right? So yeah, keep that in mind. Choosing your columns, choosing your types is difficult, and that's why we need to learn about this stuff, I guess, right? So when we come back, I'll talk to you about indexing. We'll take a quick break. 5-10 minutes is fine. Thank you. All right, looks like we got the hand working now. So, oh wow, this is another level of this is interactivity. I like it. All right, well, let's get back into it. I've got definitely more to tell you and not enough time to say it in. So we'll try and see where we can find some savings. Okay, so when I left off, we had just talked about how do we design our databases. We talked about removing duplicate data through creating multiple tables. We talked about how we can describe this design to other people using an entity relationship diagram. Talked about convention, which is meant to help us save time and effort in thinking about things. Join tables help us create many relationships. And then the schema. So the schema has to have a type, and we learned about how if we choose the wrong type, it might not accurately represent the reality we're trying to model. So now we're talking. Now we're gonna have to. We have like a slight sort of. I don't know how to put it. Indexing is something we wanted to include in this lecture, but something you won't need to really care about because it's kind of more about performance, and we're not even really making queries yet. So why do we care about performance? But this also goes into foreign keys and primary keys and all of that. And the stuff I was talking about like for later on, this is the introduction to that, to what we need to learn to make it even make sense at all, right? So forget about databases for a second, and let's talk about indexing, which is a concept in computer science that is sort of the basis for a lot of what we do. And I'm going to try and explain it to you in JavaScript rather than in databases, because we haven't learned a lot about databases, but we've learned this much about JavaScript, and so hopefully the concept of indexing, which is not unique just to databases, becomes something that you think about. Okay, so I've got these two data structures here. The two data structures contain the exact same data, but the structure is different, right? And what is the difference between these two data structures? One's an array, one is an object. Yes, exactly. And so if I needed to find a user in my data structure based on an ID that I already had, the way that I do this with an array is different than how I do it with an object. Is that everyone agrees with that? Okay, so how do I, if I have the ID RTWJ0V and I have a student array, how do I tell the computer, or how do I find that user's name for that ID? Yeah. Loop through the array? Yep, so I want to loop through the array, right? So I start by looking at the first thing. Is the ID the right one? No. Second thing, no. Third thing, no. Fourth thing. I get all the way down to the second to last item. The ID matches, so I found the entry in that array that I want, right? But that, how long does it take to do this? Depends on the size of the array, right? In the best case, it takes one iteration because it finds it in the first as the first item of the array. The worst case is that it goes through the entire array and doesn't find it. In terms of computational complexity, in terms of the length of time the computer takes to perform this operation, the bigger the array, the longer it takes. Okay, so here's my example. Students.find, it's just an iteration through. It goes through each one, and it takes the student, checks to see if their ID matches, and if it does, it gives us back that object, okay? So this takes linear time. How do we do it with the other object, though, or with the object instead? What does this other data structure provide to us in terms of how long does it take, or how do we do that lookup? Dot notation. We'll use square bracket notation. Similar, yep. Because dot notation wouldn't let us put dashes in there if we had them or whatever. In this case, dot notation or square brackets would work like this. But the idea is that I'm able to look up that value directly. I don't need to go through the entire list. I don't need to look at every single value potentially to find this one. Does that make sense? Okay, so we're going to say the array search is linear time. And the object search is constant time. It does not matter how big this student's object is. It always takes the same amount of time to grab the item out of it if I have the ID. This is a really big deal, because this speeds up our programs. If we index things, we have the ability to speed things up. Is there a trade-off here? There's a few trade-offs. One, my student's array has an order. My student's object has no order. So if I do care about order, I might need to sort after, or I might need to keep track of the order as a different data structure. Those are possibilities outside the scope of this, but that is one thing we need to think about, is that an array has a built-in order and an object does not. Another thing could be that in order, let's say we start with an array and we want to index that array. We're giving up some space. We're going to actually store a duplicate. We're storing both of these things. We start with the student's array. We convert it to a student's object. We don't lose the student's array. We add the student's object. We've just taken more space. So the trade-off for indexing is that it takes more space to keep this second representation of this data structure to do instant lookups. Does that make sense? So trade-off, no order. Trade-off, we lose space. We don't care about space, though. I told you it's cheap now. We do care about speed. Speed is the thing that constrains us. So when I think about this in terms of indexing, this is just our software. I can index any array, make it an object. But when it comes to a database table, if you are searching for something in a database table and that column is not indexed, meaning that it doesn't follow this sort of format here where we have an ID that points to that row, then it's going to search through the entire table to find that value, which is slow. If we apply an index to that, it will create this duplicate data structure. It'll do instant lookups for us. Okay? Our primary key automatically, by default, is indexed. If I look for something based on the primary key, the ID in a table, it'll just find it immediately. I don't need to search the entire thing for it because it's indexed. And so that's why this is important. We can index columns if we want at our discretion, but we don't index every single column because of the trade-offs. So we want to selectively index things. For now, don't worry about it. Your primary key is your indexed column. You're just going to do lookups based on the ID most of the time. Not a big deal. This is just an introduction to this concept, okay? And I think next week when you start to do the computer science stuff and you think about computational complexity and big O notation and all those things, think back to our conversation today about indexing and how it applies, okay? Because that's, you don't need to understand it today, but it's a good time to introduce this concept, okay? Queries. So now we need to ask our database for things. The first thing we're going to do is talk about how we create tables. So I've got this ERD, and the ERD describes the tables in a diagram, but doesn't actually create the tables for me. So I need to convert that ERD diagram now into a series of these SQL queries that will actually build the database schema for me. So here I want to build a single table. We'll call it cohorts. It'll have 4 columns in it. One called ID. That's a serial value. Now, serial is an integer. Serial is auto-incrementing. The database will keep track of that for me. The first item I put in that row or in that table will have the ID of 1. The second thing I put in there will have the ID of 2, and then 3, and then 4, and so on. So a serial value is auto-incrementing, it's unique, and it's an integer. Make sense? We're identifying the ID as the primary key. That's going to apply that primary key index and all that kind of stuff on it. So that's important. And then we're also saying not null. So these are constraints. We can define for columns certain constraints. For example, that the name column cannot be null. Every cohort has to have a name, and it would not allow us to put an entry into our database table where the name was null or empty, or I guess empty string would probably be okay, but null would not be an okay value. We have to give it a value for that. Otherwise, it will reject it and not enter into the database. Our start date and end date are just date columns. They can be null. We're okay with that. So we haven't put not null there. Does that roughly make sense? So this is how we create a table. I'm going to show you some more examples where to find those. Yes. Good point. Good point. So it's a good question. So for Calgary, here it says varchar 255. With the varchar and the char, we define what the length of this value is. And so I can say varchar 64, and it would only limit it to 64 characters. I could say varchar. I used varchar 255 because again we're not concerned about space. But you can put a value in there. You can put varchar 10, and it would limit it to 10 values. You can put char 10, and the idea, the difference between char and varchar is that varchar is anywhere between, let's say, 0 and 10 characters if you say varchar 10. But char, if you say 10, it should be 10. It should be constantly 10. Everything in that, every column, yeah, it should always be 10. It shouldn't. Yeah, that's the idea. So I don't use that very often, right? There's some situations where it might make sense, but for the most part, I don't use char. But if I had a value that's always 7 characters, then I could use char 7 and just use it for that. But varchar will work just as fine, and we're not worried about that level of performance today. We're not worried about that level of detail today. So if you're going to be doing something like a name and email phone number, just do varchar 255. It'll give you enough space, and I think that's good enough for today. Does that answer the question? Yeah, okay, good. Thank you. All right, so I've got this example here. Under my notes, there's bootcamp directory. I've got these SQL files. It's just a way for me to write queries in a file that I can run, and I can actually run this file against my database. So I can have all of these queries run against my database. It'll look like this. Okay. First thing I'm doing is I'm dropping each of my tables, if they exist. Teachers, cohorts, students, assignments, assignment submissions, and assistance requests. These are all tables that will be dropped when I run this file. And that's because I want to recreate these tables now. Create table teachers, create table cohorts, create table students, create table assignments, assignment submissions, and assistance requests. So this is a SQL file that I could run, or that any of you could run, against a database implementation. It would create these tables for you. It would create this schema for you. So this is a way for us to transfer schema amongst developers. Kind of make sense? You'll do this today with your Navy example. You'll be creating multiple tables as well. You'll see is active. Is the teacher active currently? It's a Boolean value, and we default it to true. These are things we can do when we define the schema. So that could be useful for us, right? You're also going to notice, actually I'll just show you this example here. When we create that foreign key reference, this is the way that I like to do it. My cohort ID is an integer. The reason I chose integer is because the thing that it points to is also an integer, even though I called it serial. Okay, so serial and integer have the same range, at least the upper level of the range. A serial is only positive. But this means that the integer, if I can store any of these serial values, the serial integer values, into this cohort's ID column because those data types match enough for me to do that. And then I say that the cohort ID references this other table over here called cohorts with a column called ID. That's what this is doing. You'll see in my example, I've got that here. The assignment ID references an assignments table. The student ID references a student table. Same with these ones here. My students, my students have a cohort ID. Okay. So this is how I create my references. I've added something in there called onDelete cascade. Is anyone curious about that? How curious? Okay. So it's useful for me in development. What you're going to notice, and this is something you're going to run into, so I'm just going to talk about it because you're going to run into it anyways. The order that I delete these tables could matter, right? Let's say that I have students and cohorts, and my students table depends on the cohorts table. We can all see that, right? A student belongs to a cohort, so I have a foreign key relationship. So I've created a dependency from the students table to the cohorts table. If I delete a cohort from the cohorts table, and a student points to that, that's a problem in our database. We don't want that to happen. All students should belong to a cohort. Therefore, it will not allow us to delete that table if there's something else that references it. Does that make sense? So what I could do instead is delete the students table and then the cohorts, or maybe delete the students that belong to that cohort and then delete that cohort row. I have to write code for that, right? The other thing I could do is just delete, in this case, I could actually just delete the entire students table before the cohorts table, and then all the students are gone, and then no students point to cohorts, so my cohorts table could then be deleted. I don't do it that way. What I'm doing instead is saying that when I'm going to have this cascade behavior that I'm adding, and when I delete something that this points to, also delete the thing that points to it. So if I now, with this behavior, this delete cascade stuff, if I delete a cohort, all of the students that belong to that cohort will also get deleted from the students table. It's useful for development. It's scary for me in production. Feel free to play around with it if you want. Otherwise, order your tables differently than I have. Is that a fair way to do it? Okay. Yeah, so that I put it in there just to show you that it's available, but not necessarily that it's something that you'll understand immediately. Okay. This is how we create tables. Now we're talking about records. Once we have our tables created, on any table, we want to be able to create or insert new records. We want to be able to read, or we select. That's what the term we'll use in SQL is select. We will update. It's the same in both. So we'll actually do an update call in the database to update something. We'll delete something in the database. So we can see that CRUD, those operations, the things that we've been doing with our resources in Express, for example, the URLs resource in our Tiny app. We can create URLs, we can read URLs, we can update URLs, we can delete URLs. If we were to do it with a database, this is how we translate that into SQL queries. Insert. I want to insert a new cohort into my cohorts table. Insert into cohorts, the name, the start date, and the end date. Those are just the column names in that order. Here are the values I want to put in. And I'm using ISO 8601 strings to represent those dates. So this is accurate how I could insert a new cohort. Does that make sense? Now, if I want to insert many cohorts and they only have a name, it's better for me to actually do one insert call than 4 insert calls from a performance point of view. The fewer queries we do to the database, the faster it will operate. So when I'm inserting many items in at the same time, I'm probably going to do it this way instead. And then we have select, which is where we want to spend most of our time when we're talking about queries, because this is where most of the time is spent in writing queries. It's pretty straightforward to insert stuff into a database. It's also pretty straightforward to update or delete things from a database. Where it's difficult is selecting the data from the database in the format that you want. That's where things get complicated. And in order to do that, we have 6 different clauses we use. So those are select. That's just telling the database what type of query we're making. From, tell it which table we want to grab data from. Where, okay, let's filter out some initial results. Group by, I'm not even going to bother until we get to that. Having, it's kind of like where. And then order by, that just can sort the thing at the end to be in the order that we want it to be, right? So let's go through these one by one. Select star from students would give me just a list of all the students, all the columns, however the data table had defined it. I think that's pretty straightforward, right? But if I want to, I can also say I only care about certain columns. So I will select and then give a comma-separated list of the column names from the table I want to select from. So this is pretty straightforward too, right? We're seeing here, I don't have the start date anymore. I've taken, here I want everything. Here I want everything except the start date. Cool? All right. Now, this is an aggregate function. These are very useful. But they're also probably the more complicated parts. So if I made a select from students, I got 12 results back. If I count the IDs, I get 12 because there were 12 results. So this is a way for us to maybe find out how many rows there were. I can also use things like average. It would give me the average value of all the items in that column. That could be useful, right? Max, give me the maximum value of all the rows. Min, give me the lowest value. These aggregate functions, they're applied to a result set, and what it's going to do is take a result set like this and compress it down to one value for us. Cool? So we could actually say, I want to count the number of students in the cohort with the ID 3. So here our query is really select from students where cohort ID equals 3. This is a filter now. The only results we're going to get back are the students that have a cohort ID of 3, which happen to be the middle 5 or so. So here, what's happening is it's taking all the students, it's filtering out only the ones that have a cohort ID of 3. There are 5 of them, and then it counts those results for us, and we get 5 back. Cool? So the filter happens before the count here. So here is, I think, the most complicated part about SQL queries. So I'm going to try my best to explain in a simple way. My goal here is not just to get the number of students in one cohort. I want to get all of the students. I want to get a count for each cohort. How many students are in each cohort? So I have to group things up now. Let's look back at this data here. If I were to group these students by cohort ID, how many groups do I have? That's right. The first one has 1 student in it, right? So let's think of groups as buckets. So I've got 4 buckets there. And I guess each time I come across a new cohort ID, I'm going to add a new bucket. But for this example, I have 4 buckets. When it finds a student that has the cohort ID of 1, it puts them into the bucket with for cohort 1. Finds a student with cohort ID of 2, it puts them into the bucket 2. Don't forget that these might be in a different order in the database. It's not necessarily, this looks pretty straightforward, right? But there could be thousands of entries into the database, and it could be out of a different order. So really it's going to go through everything. When it finds that cohort ID, it puts it into the bucket. And so ultimately we end up with is 4 buckets with different number of students in each one, right? All right. So when I do this count ID, it's actually going to do it once for each bucket. And it's going to count how many students are in cohort 1, how many students are in cohort 2, how many are in cohort 3, how many are in each group is really what we care about. When we group things, then we can count those things and convert it down into one value. So here we're getting the number of students in each cohort. Does that roughly make sense? Okay. If let's see, is there something better to? There's nothing really better to group by here. If I group by the name, everyone's name is pretty different, so we'd get 12 different buckets. If we group by ID, we'd also get 12 different values here. So grouping's about taking this result set here, this student set, and breaking it down into these different chunks or groups, and then being able to apply maybe an aggregate on each one of those groups. I've also added here count ID as student count. So you'll notice here I didn't put an as. So I can alias things if I want. I can say that this count ID thing has a different name when I actually get the results back. That's what we're seeing here. Select count ID as student count. So it actually is going to write student count as the top of that column. Whereas over here, it just calls it count because that's the aggregate we used it. So you get to rename these things if you want. Pretty useful. Okay, so here, having, I said it's a lot like where, except it happens after all the grouping and the counting and all that other stuff. Whereas where happens first, and it gives us a filtered list, and then we can group and count it. Having will allow us to create these groups, and then create our aggregates, and then then filter based on the having, or based on that count. So here, if I don't use having, I get all 4 cohorts, everyone, student count 1, 2, 5, and 4. Here, it's only count where the count is greater than or equal to 2, so cohort number 1 is removed from this result set because they did not have a count. They had a count of 1. Make sense? Okay. And then we can order at the end as well. Order by count ID if we want, or start date, or end date, or name, or order by anything. But if we're going to order by an aggregate, we have to put that count ID right in there again. Order by count ID, and we're saying descending so that the higher number is on top. Yeah, I guess that kind of makes some sense. So the last thing is I'm putting a where clause back in here. So this is going to use all 6 of them. We're going to select from the students where the start date is greater than April 1st, so it's going to leave out any student that started before then. And then it's going to group those students by their cohort ID, so we're going to get 3 groups out of it. And then we're saying, well, only cohorts, actually, I don't think no, this one's kind of a bad example because the having is kind of useless now because the cohort 1 was removed by the where clause. So let's say we group, then we can order, or then we can filter it one more time, and then we can order. So this is kind of how we would see all these things used together. And that would, I don't know. I'm going to do more of these examples this afternoon. That's really what this afternoon is about, is more complex examples like this. Because, like I said, selecting is the hardest thing, right? Okay. Questions about this before I move on? We're good? Okay. So I have this update and delete next to a fire. Why would I do that? Why would I use this imagery here? Yeah. Unsafe operation is a good way to put it. I'd say, yeah, if I have a high likelihood of getting burned if I use these incorrectly, and that could be in the production database. That could be quite bad for your business. So let's talk about it. My first query, what does it do? Yeah. Yeah, update all the users' passwords to the exact same thing. So congratulations, all users now have the same password, and it's a really horribly insecure one, right? And this might happen if you are, let's say you have a customer and they're saying, I can't log in, and you're like, well, try the password reset, and they're like, well, I did. Like, okay, well, I'll reset the password for you, and then you can go change it. So I'm just going to set it to 1, 2, 3, 4, 5, 6, and then you can quickly go change it, right? And then I run this query, and now everyone has that password. And how do I get back to what their old passwords were? I better have a backup. Because I don't know what their passwords were. I don't know what even when they store them, I don't know what they are. So really careful of this. Delete from users, that's going to delete the entire users table. Delete from users where ID equals 12, that would delete just the one, right? So always use a where clause. Just always put one in. Even if you want to delete the entire users table, delete from users where true, where 1 equals 1, where something exists, to be so that you're not just running these queries kind of haphazardly. So even if you want to affect the whole table, put a where clause in for that. I had another good suggestion from someone, a student who had worked with databases before, and they said that their rule at their office was whenever someone was going to do an update or a delete, they would actually write the query as a select first. And then they would see all the rows that would be updated or deleted, and then they'd be able to confirm, yeah, that's the right where clause. That's the right, I haven't missed something somewhere, right? So you want to kind of be really careful with the update and delete, because these are the things that could break your database. Selects are safe. Okay. Well, good news. I've got a little. I had more time than I thought. This is great. So this is the last subject for this morning. It's joins, joining multiple tables together, so that when all the way back here, when I want a result that comes back like this, I can get it from a database structure that looks like this. The way that I make it so that I get data out of the database in a structure like this, but still store my data in a structure like this, is through joins. I join these two tables together, and I can join students and cohorts together, and I can come back with a result that actually has a list of students and their cohort names. So here, we do this with a join. There are 5 joins, and we only care about 2. Does that make life easier? I think so. We care about the first 2, the inner join and the left outer join. I'm going to very lightly talk about the others, and more in an effort to tell you why we don't care about them. Right? So let's start off and make sure that if we come out of today understanding the difference between an inner and an outer join, I'm very happy. That's a good goal. So this is where ambiguity comes in. And this is also why I suggested that you name your primary keys as just ID. Because when we start to join two tables together, we now have to identify columns from two different tables. And if those columns have the same name, which I told you is completely valid, then we want to disambiguate which column we're actually talking about. And we do it with this table.column syntax. So the table name is students, the column is ID, students.id. Can you imagine if we put student ID there? It would be student_ID. That's redundant, right? We don't need that. Students.name and cohorts.name mean different things, come from different tables, so we disambiguate them by using this table.column syntax. All right. Inner join. I want to take two tables, and I want the result back that gives me a list of the students in the cohort they belong to. Make sense? So when I do an inner join, what I'm going to do is I'm going to say select star from students, or let's say select students.studentName, cohorts.cohortName from students. So I'm going to start with the students table, and I'm going to join cohorts on a condition here. The condition is that the cohort ID matches the student's cohort ID. So it'll go through and it'll say, okay, I got this student here, Sam Billings. Sam has a cohort ID of 1. I'm going to look in this other table now for a cohort that has an ID of 1. Do I find it? Yeah, okay, great. And so I grab that, and the data that I care about is the cohorts.name. So I take that out and I put it with Sam, and now I have Sam Billings, cohort name, February 12th. Make sense? It's combining those things together. Now now we look at the next record, Susan Hudson. Cohort ID is null. Do we find a cohort ID with the value null? We don't. And in inner join, this means everything to us. When that condition is not met, it does not make it into the final result set. That's why we don't see Susan in that result set. It's because Susan's cohort ID doesn't exist. So on that join, the condition isn't met. Therefore, she is left out of the final result. But Malloy, he's got a cohort ID, number 3, April 9th, bring that in, put them together, join them, and here's our result. This is what it actually looks like when we make the query. Make sense? From students, inner join cohorts on the condition that we're joining on is what's important. When that condition is not met in an inner join, what happens? Sorry, I need louder. It's left out, exactly. With an inner join, when the condition is not met, it is left out. So this does not give us a list of all of the students and their cohorts, just the students that are in a cohort. I could use an outer join, and an outer join would give me a list of all the students and their cohort name. And if they are not part of cohort, we're going to get null back. So this is how it's going to work. Same deal. We look at Sam Billings. Sam Billings has a cohort ID of 1. We find that ID in the cohorts table. We add them together. That's our first result row. We look at Susan Hudson. Null. We don't find that in the cohorts ID. But because it's an outer join, we still include it in the result set at the end. But we have to put null in for the cohort name because we never found out what it was. Does that make sense? So the values, when it doesn't meet that condition, the things that it's getting from that other table will have null values. And then it finds it for Malloy, no problem, adds it in there, and we get 3 results back. So this is the main difference between an inner and an outer join. Is an inner join, when the condition is not met, it is left out of the result. And an outer join, when the condition is not met, it is kept in the result, but we get null values for those things that we didn't find. Make sense? Now, there's one more thing here, because it's actually a left outer join. It's not just an outer join, it's a left outer join. And the reason why left is so important is because we want to tell the query engine which table we want all the results for. And in this case, it's the students table. We want all the students, no matter if they're in a cohort or not. So we're going to left join with the students on the left side of the join operation. That's what it means. Left join. The left side of the join operation is the students table. What's the right side of the join operation? Cohorts table, exactly. So this is a left outer join, students and cohorts, with the students table being the authority on which rows actually make it into the result set. Does that kind of make sense? Okay. Now, which table is the left table now? That's right, exactly. So that's important, where I put these things. That matters. Now what it would do is it would actually go through, oops, actually I can go back to it. Now what it would do is it actually go through these, so it would take this cohorts here, and it would say, okay, I got this cohort name Feb 1, and I'm trying to find a student that has a cohort ID of 1. Do I find that? Yes. So what I'm actually going to get is, Feb 12, Sam Billings Feb 12. But then when Susan Hudson doesn't match, when it gets down here and it says, I've got this March 12 cohort with an ID of 2, there's nothing in here with an ID of 2. Therefore, you'd actually get student name null and cohort name March 12th. So it's actually just the opposite of what we did before. So the reason why we have a left and a right outer join is for completeness. But we don't actually need both those things, do we? Because I just showed you how you could do the same thing, or you could do both of these things with a left join just by swapping the order of those tables. So here, this is a left outer join, students and cohorts. So right outer join, the right is the cohorts. It would operate no differently than what I just did. So mostly for completeness, I don't use right join. I just kind of put the tables in the order that I want them, and I use left join. The other thing you're going to notice from this is that here I did inner join cohorts. Inner is optional. I don't need to put the word inner there. So you might not see the word inner. If it's just join, it's an inner join. Okay? Now here, right outer join, outer is the optional word. And the thing that is not optional, if you want to do an outer join, is the left or right designation. This would accomplish the same goal. Left join. It tells the query engine that it's an outer join because it's saying it's specifying that the left side matters. Whereas here it's saying it's an inner join, but if I left out the inner, it's still just a join. So you might see both these things. Yes. Is it considered bad practice to leave out inner? I do it. So take that for what it's worth. Yeah, I just do join and left join for my practice because I don't. The only reason I might not do that is if I had people working in the code base that I'd be worried that they didn't know the difference, but I'd probably just rather teach them the difference than do that. Yeah. But it's not bad practice or good practice either way. The main thing is to choose the right type of join. Do you need an inner join or do you need an outer join? And to know that one of them is going to leave results out and one of them will not. That's what matters most out of this is that distinction. Okay. There are a few other types of joins out there. I put them in my notes so I can let you take a look at that if you want. So the right outer join is just the opposite. We can see the results here, what that would look like. So this is when I do the left outer join with students. This is when I do the right outer join. We got this thing called a cross join, which is kind of weird. It gives us the Cartesian product. It's actually going to give us, here I'll run it. It's giving me a list of all the students and all the it's giving me essentially the number of students multiplied by the number of cohorts in terms of results. That's, I mean, I've never used it. I don't know if that's going to be useful for you, so I'm not going to bother spending much time on that. I can do this cross join. The other way I can do this is select star from cohorts, students, so I can select from multiple tables at the same time, and that's what it accomplishes. if I were just to do this select star from cohort students and then put a where clause on it, this where clause looks a lot like a condition that I would use in a join. This is the same as me doing an inner join. So inner join is shorthand for a selection of all possible combinations, filtering out only the ones that actually match this condition. And then there's a bonus section which you can read on your own. So there's also like a full outer join. Don't worry about that. Don't worry about that. I hope this prepares you for today. If you have questions, please let me know. I'm here till 5 or so. And yeah, the assignments today should help try and solidify a lot of the things that we talked about. Reference my notes. The slides are there. I've posted the video in the in both channels. So as soon as I kill the stream, YouTube's going to process that video, and then it's going to be available to you to review anything that we talked about if I went too quick or too slow or whatever, right? So send me feedback on Slack. It's Jensen. You can send it to me specifically. If you don't want to give it to me directly, if you want to be anonymous, give it to Davey, and then he can give it to me anonymously. That's fine with me too. I like to ask maybe more questions, but if you don't want to give it to me directly, I'm fine with that. Important thing is that I get the feedback. If there are no questions, that's it for me today. Oh, I got Raymond. Oh, is this going to go?
Jensen Number, thanks for an Amzing lecture.
Amzing. Yeah, you're welcome, Raymond, and welcome, Calgary. And it's good to see everyone, and I will be back. Not. That thing's killing it, by the way. I really like this. Yeah, I can't wait to see the next iteration, Sam, wherever he is. Cool. Thanks, everyone.